and other one was I think the something to do with sorting, right? So we'll take a look at them first. However, I think we also got an incorrect answer for one of the questions, right? So I will go ahead and then share that part as well. So let me see where I got it. Okay, there we go. So let me go ahead and share my screen here, and we'll get started with that particular problem. Okay. All right. So are you able to see my screen right now? Are you able to see my screen right now? Okay, clear, right? No blurs. No, it's not. You're not getting a blurred screen, right? Okay. All right. So this is the problem, the number of permutations and that we were looking at, right? So this is something that was giving us an incorrect answer. So apparently, I got a version of that which actually works fine. So let's actually go ahead and run this, okay, right? So we are supposed to get two permutations here, right? One is for this particular input, right? So this is going to be obviously 1, 8, 17. And of course, we need it to be 17, 8, and 1. Okay, so this is what we're supposed to get. Let's see if we can get that now after running this one. I'm going to go ahead and enlarge this a bit, right? Sometimes it's difficult to get. Oh yeah, there we go. Okay. So I'm going to say node permutation find. I have a typo here. It should have been permutations, and there we go. There we go. So we get a count of 2, right? That's what we were looking at, right? So similarly, yeah. So this is the permutations problem, the exhaustive search problem, where we're looking at all the possible answers, and out of those answers, we are looking for the right answer here, right? Given a certain input, right? So this is going to be that particular problem, and after this, we're going to go ahead and then look at a few more problems here, and so this is, as I was mentioning, this is all on. This is going to be using the concept of recursion and also the backtracking, right? So that is something that you got to essentially appreciate and remember when we encounter these kind of problems. Okay. So this right here is the backtracking part. This is what causes the backtracking. So can you tell me where else can backtracking be used? Any examples that you can quote? Any examples that you can quote? So you would have heard about online games, right? Yeah. So something like, let's say if you're asked to have 2 players playing, let's say, chess, right? The computer has to determine which are the right possible combination or permutations of moves, right? Based on which particular, let's say, player it is. It could be a, let's say, a minister. It could be a king, queen, or a camel or a horse, right? Based on that, you move differently on the chessboard, right? So those kind of things, right? That will involve backtracking. So let's say you're trying to solve a Sudoku problem, right? For a, let's say 8x8 board or a 3x3 board. That would involve backtracking as well, because we are trying to look at all the possible options from the current position and then looking at the correct solution, right, at the end of it. So that would involve backtracking. So, but generally, these kind of solutions which involve backtracking are very expensive because they involve looking at all the options and finally coming up with the right options out of all the possible options, right? So they can be very expensive in terms of when it comes to the performance, right? Okay. So with that, let's go to the next problem that we want to solve here. And I'm going to share my screen. All right. So it is called threesome closest. So we are given an integer array of numbers of length n and an integer target. Find three integers in num such that the sum is closest to the target. Okay. Return the sum of these three integers. Okay. So you may assume that each input would have exactly one solution. Okay. So we are given a target, right? Let's take a look at the example. So we're given a target, right? This target is 1, and this is the input array, right? And we need to find out a triplet, right? That, and the sum of which would be equal to or will be closest to the target here, right? So in this case, the target is 1. And if you look at these two numbers, if this numbers, right? If you take any of the three numbers, the closest to 1 would be 2, right? If you sum them up. So for example, let's say you take the first three numbers, -1, 2, and 1, that the sum of that would return, let's say 2, right? And that would be the closest. Or for that matter, and if you look further, let's say you take 2, 1, and -4, and that would be further away, right? So the closest would be 2. That's what they're trying to say here, right? So let's see if they have given some more examples here. Sample input 2. So let's say 0 and 0 and 0, and the closest here, and the target here is 1, and the closest here it's going to be 0. Okay. All right. So how would you solve this problem in the first place? If it were to be the brute force, right? How would you solve that is a question, right? Again, every problem would have a brute force, right? And there would be an optimal solution as well, right? So let me bring up my whiteboard here. Okay, let me bring up my whiteboard here. There we go. And okay, so we have a target, right? We have a target, and we have an set of input numbers. So let's assume that, let's take the same example, right? Numbers from the same example. Let's take -1, 2, 1, -4, right? -1, 2, 1, and -4, right? So we need to find a triplet, right? whose sum is going to be closest to this one. So let's say the target here is 1, right? Let's assume, take it again from the example. We need to find a set of triplets whose sum is closest to this particular target. So if you look at it visually, right? So let's say I take the first 3, right? So let's keep track of them, right? So let's say these are the triplets, and this is going to be the sum, right? So let's say I take -2, 1, and 2, right? So -1, 2, and 1. So here the sum is going to be 2, right? And if I take 2, 1, -4, what's going to be the sum here of these triplets? This is going to be 3 and -4, and that's going to be -1, right? So the closest here would be 2. That's what so the closest sum that we can think of here would be 2, right? So that's what they're looking for right now. And there are multiple ways. Yeah, the closest sum. Closest to this one. Closest to this one, right? You cannot say -1 because after 1 you have a 0 and -1, right? So closest would be 2. So if you look at the distance, it is 1. Here it has to go through a distance of 2 to reach -1, correct? Okay, makes sense? Okay. So if you look at the problem here, right, how would you actually look at it? Let's say if you had to do a brute force method, right? So here we're looking at, so the brute force way would be to have 3, let's say, pointers, right? So essentially you can have this one as the ith pointer, and then this one as the jth pointer, and this one could be the kth pointer, right? So we can essentially have a 3 pointers which essentially run in 3 for loops, right? So first one would run from, let's say, I to, let's say, 0 and I less than, let's say, this length. Let's assume that, and we know the length is stored in len, let's say. So len is going to be input length dot -1, right? Let's assume that it's actually pre-computed, right? And so let's assume that's a len, and we have to go till what? Len -2. We cannot go all the way to the end of the array, right? Because at the end we want to have 3 elements, right? So we need to be, our first loop has to end at the third element from the last, or the third element from the end, right? So that's why I'm saying len -2, right? Okay, hold on. Made a mistake here. I less than len -2 and I plus plus, right? Similarly, we will have j running from, let's say, I plus 1, right? And j less than len -1, right? Right? And j plus plus, of course, right? And finally, we have k running from I plus 2 and k less than, okay, actually, it's turning out to be very messy here. Okay. K is equal to I plus 2, k less than len, of course, right? K, oops, len and k plus plus, right? So this could be your brute force, actually, right? Here you check whether input at I plus j plus k it's going to be a sum, and you can maintain an external value here, which is going to be the min, right? The closest, right? And then we can keep essentially computing that over and over again until we finish going through the scanning through the entire length of the array, right? And what's going to be the complexity here? So this could be a cubic complexity, right? So essentially it's going to be order of n cube, right? So which is quite expensive, right? So how can we bring it down is the question here, right? So so yeah, this can definitely lead us to some kind of solution, but obviously this is going to be the time complexity is higher than required, than what we would like it to be, right? So the question now is, how do we actually bring it down, right? So let's take a look at that. So if you look at this, right, let me actually take the numbers one more time here. So that was -1 and is where -2. Oops, I forget. -2, -1, 2, 1, -4. So let's actually go ahead and sort these numbers, right? So I'm going to say, if I sort this one, right, I'm going to get something like this: -4, -1, 1, and 2, right? Okay. So this is going to be sorted, and what's going to be the complexity here? If I sort it, it's going to be n log of n, right? That's going to be the time complexity, right? Order of n log n, right? So with this in place, what I can do is I can go through the scan through the entire array, right? And then I can have internal loop, which is going to essentially have a left pointer and a right pointer. And every time we calculate the sum, we'll check if it is closest to the sum, right? So what I'm going to do here, I'm going to say for let I is equal to 0, right? I less than, obviously, num length dot -2. I'm going to say len -2. Doesn't go all the way up to the end, right? And then I plus plus, right? Okay. So I'm going to have, and within this, right, I'm going to have a left pointer and the right pointer, right? So let's say this is our I pointer here. This is going to be our left pointer, and this is going to be our right pointer, right? So every time, and then, so essentially what happens is that I will be adding up I plus L plus R, okay? So what I'm going to do, what's going to happen here, I will check if this is, how close is this to our target, right? How close is this to target, right? So essentially, I will look at the sum of all these numbers, and I will check if sum is equal to target. If sum is equal to target, we return a 0, right? Otherwise, we find the diff, right? And we check the min, whether it's a minimum diff, right? So we'll maintain a min here, right? So this min here is going to be, let's say, some infinite number, right? So let's say it's going to be infinite. Right? Then we can check if the sum is less than infinite, right? So it is going to be that, and then we will essentially maintain that sum here. So closest sum, that is, right? So this is going to be the temporary sum, right? We'll then check it with the min here. If sum is less than min, right? That's going to be the Okay, it is not the sum. It is going to, so let's say that this is the sum, right? We will say sum minus the target, that is, right? So the sum minus the target, and it will take the diff, rather the absolute of that, right? The sum minus target. We'll compute the sum minus target, right? And we'll take the absolute of this one, not the negative, right? And we'll check the result of this with the min value, which we're maintaining here, right? And then we'll go through the entire loop and check if the min is more than diff, right? And then we'll compute the uh, following, um, uh, we'll compute the absolute here, right? So if the min here, right, is, let's say if the sum here, right, it is greater than the target, right? What do we do? If the sum here is greater than the target, right, which is going to be 1, what can we do? We can actually go ahead and decrement our right pointer, right? So because we know that this is sorted, the right pointer will always be the having the highest value, right? So we keep coming inwards. Okay. Similarly, if the sum is less than the target, what do? We move our left pointer inwards, right? And then finally, we reach a point where our sum will be closest, or until left is less than r, right? That's how we run the pointers here. When they cross when the pointers cross each other, we will essentially end our processing, right? Okay, so let's actually put this into coding, right? And then we'll understand what we're trying to do here. Okay. Actually, someone was waiting. I felt. Hope you guys let him in. Someone was waiting. I felt. Okay, this is part 4, and this is going to be 3 sum underscore global cest. .js. Okay. Okay. So let me go ahead and start coding here. So I'm going to get a function, and that's going to be called sum closest. This is going to be a function, and that's going to get a nums array, right, and a target. All right. Okay. So the first thing what we want to do is, because we want to reduce the complexity from, let's say, cubic complexity to a lesser complexity, we will go ahead and then sort this array in a ascending order, right? So I'm going to say nums dot sort, and this is going to be a, b, and a minus b, right? This is going to be sorting it in ascending order. Okay. As well, this has the complexity of order of n log n. That's the least, right? Most of this, the sorting algorithms that we know of, the best that we can get here is n log n, right? So which sorting algorithms have you learned in your earlier lessons? Do you remember any of them? Any of the sorting algorithms? Bubble, okay. Insertion, okay. Mm. Yeah, actually, yeah, merge and quick sort as well. Yeah. Mm. Yeah, bubble and insertion selection are again expensive algorithms, right? In terms of time complexity. Merge and quicksort, even heap sort to an extent, are better algorithms from a time complexity, right? And yeah, quicksort. I think merge sort has an um, additional space complexity as well, because they actually do a they create additional arrays, right, internally to get the sorting done. So merge sort has that additional complexity in terms of space complexity. Quicksort is in place, so it can be pretty fast as well. It doesn't use any additional space, right? That's going to be one of the key factors. In case you're required to use less space, you go with a certain algorithm. You have a lot of space and you want to essentially use your computing power, and then you have a very huge data to work with. Then you choose another. Okay. All right. So we've done with the sorted tiers, and then let's keep track of the min, right? Which is going to be going to give us the minimum number, which is closest to the 3 sum, right? So I'm going to set it to infinity. Okay, this is going to be JavaScript's way of saying this is infinite. This is a constant in JavaScript, right? Let me go ahead and close this one out momentarily. Okay, didn't close that apparently. Okay, super. So what do? We actually open up a for loop here, right? And I'm going to say this is going to be running from 0 and to length -2, right? And I++. All right. So, and then we also want to know what is going to be the left and right pointers, right? We want to maintain the left and right pointers. So I'm going to say left, left is equal to the next number that is next to the corresponding I, right? So I'm going to put that as I plus 1. And right would be the last element, right? So I'm going to say left, right is equal to, and that's going to be nums dot length -1. Okay. All right. So at this point in time, what we want to do is we want to go from left to right, right? So I'm going to say while left, we want to run this loop only when left is less than right. Moment they overlap, it comes out, the loop is going to break. Okay, so left is less than right. Okay, what do? We want to find the sum, right? I'm going to say const sum equal to, it's going to be nums at I, oops, nums at I, right, plus nums at left, right, plus nums at right. Okay, and if the sum is equal to target, right, we have nothing to do, right? So we can say return 0 straight away, right? Because that's the closest you can get. Otherwise, we want to find the difference here, right? So I'm going to say let diff. We're going to do the absolute here. So I'm going to say math dot abs and sum minus the target. Okay. All right. Here we check if we need to maintain a min here as well, right? So we're going to say if min is less than, rather min greater than diff, min greater than diff, what do we do? I think we're maintaining another one here, which is called result. So give me a moment here. I got my cursor got stuck for some reason. So if this is the case, we can actually maintain another we're maintaining, yeah, address. Say result is equal to sum. However, okay, this is fine. And the next thing we want to do is we want to check how close are we to the target, right? So if sum is greater than target, what do we want to do? Sum is greater than the target. What do? We want to decrement the right pointer, right? So I'm going to say right minus minus. Okay. Else, we want to decrement or increment the, if the sum is less than the target, or maybe let me make it explicit here. That way it's more readable. If sum is less than target, what do? We will go ahead and increment the left pointer. That's all there is to it. And finally, we just go ahead and return the result here. So this is our while loop, okay? And this is our for loop, right? And we'll go ahead and then return the result. Okay. All right. Actually, we should say min is equal to diff as well, because we need to essentially look at the new diff, new min, right? So yeah, I think that's what we're going to do here. Okay. All right. So let's actually give this a run. I'm going to go here and then give it some test data. So I'm going to say const nums is equal to, this is going to be an array, and -1. We'll use the same numbers, -1. Okay, can you hear me all right? I think it got stuck for some reason. No, sorry everyone. I got disconnected for some time, so I'm back. You're able to hear me all right? Are you able to hear me all right? Okay, super. Okay. Maybe I have some issues with my internet today. So what I'm going to do is just going to turn off my video. That way, there is no disturbance, right? Okay. Okay. So all right. Let me go ahead and then reshare my screen. Okay, I'm coming to that, Hariharan. I'm coming to that. Just give me a moment here. So just how we are finding the closest. Okay, so closest is we try to find the sum, right? And if the sum is going to be, let's say, equal to 0, right? If sum is equal to target, right? And we keep on, that's going to be the closest that we can get, right? Otherwise, we keep on essentially finding the result, right? We essentially have a min here and then the diff here, right? So every time the diff is, let's say, decreasing, we actually capture the result here, right? Correct? That's going to be the closest. You get it, right? Okay. So we are actually capturing that logic would be here. If the min is less than diff, and we're actually every time we get a new minimum diff, we are capturing it here, right? So that's how it becomes the result would be, and then finally we essentially say the result would be the sum, and we return that sum, right? Okay. Let's go ahead and run this. I need to get some test data. Okay, there we go. -1, 2, 1, and -4. Same data as before. And let's say target is going to be equal to 1. Okay. And I'm going to say console.log. It's going to be 3 sum closest there. Closest here. It's going to be the nums and target. And hopefully we'll get the right answer here. Otherwise, we need to do a little bit of debugging, right? Okay. I'm going to enlarge this a little bit. Difficult to find where this particular thing is. Okay. So I'm going to say, I'm not sure where we are right now. This is going to be part 4, right? Okay, there we go. And let's say node 3, sum closest. It is -2. That's the closest. Why is that so? It should have been +2, right? But I thought we did an absolute here. Because if we take these numbers, -2, 1, and 1, they won't be a -2, so there's no -2 here. It cannot be -2. Let's actually capture the sum here, right? Console.log. Let's say sum, and obviously the diff, right? Let's go ahead and do this. Diff is 3, sum is -2. Okay, when did we get sum as -2 here? It's fine. So, okay. Okay, let's actually do another one here, console log. And this is going to be equal to, let's say, n1 is going to be equal to nums I, nums at I, and 2, it's going to be nums at left, right? And 3 is going to be nums at right. Okay, let's see what we get. N1 was -3. How come? Should have been -1. Okay, if I do this right now, say n1 is nums I0, so it should be saying, what's the input here? Maybe we'll just print that as well, console log nums, right? Okay, let's print this. Nums dot sort. Yeah, but we don't have -3, right? We don't have -3. Remember, it's saying n1 is -3, so nums is -3, 1, 2. Where is it getting it from? My goodness, something is obviously wrong here. Nums and target. Okay, let's actually console log nums. Oh, it's 1, 2, -3. What? I'm not sure. Oh my goodness, it's crazy. So nums and target. Oh my goodness, this is left that we were feeding. I missed the comma here, and that was causing an issue, right? Okay, good that we actually got through this problem. Okay. All right, super. So this is, let's look at the time complexity. I think we looked at it as well, right? We have a time complexity here of, let's say, order of n log n, right? However, which is for the sorting, of course. But if you look at this, right, we are having two loops here, right? So one that goes from, let's say, the first element to the almost end of the array, and other one which is essentially scanning through left and right, again, which is from one end to the other end, right? So we can say that potentially this is actually n log n plus order of n square, right? This is going to be the time complexity. Overall, this is going to be, if you have to round it up, it's going to be O n square. Right? So which one is better, O n squared or O n log n? Or, I think I let the answer out already. O n log n is better or it's worse? No, O n log n is better, right? O n squared is worse, right? So if you look at, let's say we take the example of sorting, right? We have quicksort. I'm sure you've looked at it. You've learned about quicksort. Quicksort has a complexity of n log n, right? But if we provide a certain kind of input, right, it can worsen to n square. Okay, so n log n is always better. Okay, all right. And obviously, we don't have any space complexity here. This is going to be space complexity of order of 1, I would think. Right? We don't have a whole. This is all these variables are constant times, constant complexity in terms of space, right? Constant space complexity. So we don't have additional space complexity here. Okay. All right. So let's move on to the next one, which is going to be another interesting problem here. Okay. I'm going to open my screen here. Yeah, this one. So, all right. I think we looked. What is this one actually? Coin change we looked at, right? I think yesterday we looked at the coin change problem. So we already done this. And other one was, I think the last one here is this one. So essentially, Sachin used to watch series in a weekend, and in each series having n number of seasons only. N number of seasons, and only selective seasons are most interesting to watch. Given AI as an interesting season for series N, and the series seasons are shuffled, so help Sachin to watch the season in order. Okay, so essentially saying we have an array of, let's say, seasons, right, like this, right, and we need to essentially sort them in the right order, right? So for example, given this particular input, right, we need to sort this, and this would give us an output of this 1, 3, 5, 7, 8. Similarly, if we give an input like this is going to be this. So this is essentially a sorting problem, right? We use a sorting algorithm to sort this, and as you mentioned, we have different kinds of sorting algorithms here, right? One is the, let's say, you mentioned about bubble sort, insertion sort, selection sort. And what's the complexity of those things? Any thoughts? For them, it's going to be order of n square. And I think for bubble sort or one of them, there will also be a lot of movement of data, right? We actually have to move the data inside the array. So there will also be that complexity, additional complexity. And so those are very expensive sorting algorithms and generally used for, let's say, for educational purposes, right? You want to start with sorting algorithms, and you start with bubble sort and gradually go all the way up to more, let's say, advanced sorting algorithms, right? Which are more, which are better in terms of performance, the time complexity, right? So that, with that said, we have quicksort as well. We have the merge sort as well, right? And essentially, have you learned about merge sort and quicksort as well in your lessons? In your earlier lessons, have you essentially had a chance to look at the merge sort and the quicksort? You have? Okay. So what's the difference between the merge sort and the quicksort, if you can recall from your Any pros and cons? So what are these algorithms called, by the way? These are called divide and conquer, right? Divide and conquer. All right. And they also use recursion. Because it's divide and conquer, what happens is that they try to divide the problem into subproblems, right? And each subproblem is again divided into subproblems, right? And so this is done using recursion, right? They use recursion extensively, right? They use recursion. Oh, yeah. And so that's one commonality between those two. And after that, you will essentially, there will be some differentiation here, right? So as you mentioned, it's going to use pivot, quicksort, and merge sort obviously uses a different mechanism, right? It does a merge and then does a sort, right? It uses both of them. And here, this uses additional space, right? This is in place. Quicksort is going to be in place. This is going to be not going to be in place, right? It's not in place. So when we say it is in place, what do we mean by that? Any idea? When we say quicksort is in place, what do we mean by that? It means that it is not going to allocate additional space, right? And we just use pointers to swap elements, right? That's what we'll be doing. Okay, that's what it's in place, and that's why it is space complexity is better in case of quicksort here. Okay, all right. And what else can we do here? So this is in place and this is not in place, merge sort. And obviously the complexity here is going to be n log n in this case. This is going to be n log n as well. However, in worst cases, it can turn into n square as well, right? But not so much with merge sort. Okay, that's something that we need to look at. But for smaller data sets, right? I think quicksort is going to make a it can be pretty good. For bigger data sets, probably the merge sort would make a good choice. Okay. All right. So with that place, let's actually understand how we can implement quicksort. Okay. I'm going to take an example here, right? And then after that, we will go ahead and then implement the IDE. So let's take this example. Okay, I'm going to take this example. So this is going to be 2, 7, 8, 6, 4, 1, 9, 3, and 5. Okay, let's take this is our input array. Okay, so and I would be explaining this with respect to the quicksort, because that's what we're going to implement. Okay, and so let's say that we assume that we have this particular input array. In quicksort, what happens? We actually take the input array and then take a pivot as it, we identify a pivot element, right? So let's assume, and it can be any element, right? But let's assume that we take the rightmost element as the pivot element. Again, it can be any random element. Let's say I take the rightmost element as the pivot element. So after this, what happens? I go through the entire array and find the appropriate position for this element phi, all right, such that that will be the final position for that particular element, right? So let's say in the first iteration, I will choose 5, which is the rightmost element in this array, as the pivot element. And after processing this, what happens? I will end up with this particular array. So for example, it's going to be 2, 4, 1, 3, 5, 8, 9, 6, and 7. Okay, so if you look at it right now, 5 is in the correct position, right? And everything before 5, right, is less than 5. Everything after 5 is greater than 5, right? So all these numbers are greater than 5. These numbers are less than 5. All right. So when after the first iteration, whatever pivot has been chosen, it will be placed in its correct position, right? This will be the correct position. So now we know that 5 is in the right position, right? In its final position when it comes to the final output. However, we also know that the numbers here are still unsorted, right? If you look at these numbers, they're still unsorted. Okay. So what we do, we apply the quicksort again to these two halves. Okay. So what we do, we take 3 as our pivot element in this case, right? So what happens if we take the 3 as the element? We actually produce a output like this. It's going to be 2, 1, 3, and 4. And here it's going to be 6, 7, 8, and 9. Okay. Okay, sorry. Yeah, I think that's about right. So this is 8. So this is going to be, again, another thing to note here is that this is a multi-branch recursion, right? Because we are carrying out recursion in 2 places. So this is going to be a multi-branched, another thing for us to remember, multi-branched. Okay. So essentially, we're running the same quicksort process on a sub problem here. Remember, we talked about this. This is a divide and conquer algorithm. So we divide the problem to sub problems and run the same algorithm on top of each sub problem, right? And eventually merge all the results. That's going to be the typical divide and conquer concept or term, methodology, right? Okay. Finally, so we choose 4. So right now, 3 is in its final position here, right? After, okay, someone is actually knocking on the door. Let me take a look at this. Okay. All right. So so right now, 3 is in its final position, right? So we can then do quick sort on numbers to the left of 3 and to the right of 3, right? Similarly, 7 is in its final position, right? We can do quick sort on numbers to the left of 7 and the right of 7, right? Okay. So what happens here? We can, and then we can sort this one. What does this lead to? This is going to lead to 1, 2. 3 is already sorted, and we get 4 here. And similarly, we get 6 here, and we get 8 here, 8 and 9, right? So so after this, right now, we got from here, right? We want to do this until we are reduced to a single element, right? So right now, 2 is the pivot here, right? So we can say there is nothing to sort here, right? So this just leads to 2 here. And similarly, 8, 9 is the pivot element, so it just leads to 8 here. So whenever we actually run into a single element, it is already sorted, right? So we don't have to do anything. It is going to be in its final position, right? So that's how we actually apply the quicksort algorithm here. Okay. Making sense? Okay. So let's go ahead and then code this one out, and we'll understand it much better when we actually go through the actual coding. All right. Okay. So I'm going to call it quick sort. Okay. Right. Okay. So let's get started then. Yeah. So remember, there is also the concept of partition here. So just so that, so when I say partition, right, when we look at the at 5, right, as a pivot element, we will try to find the partition ID for this one. So when I say partition ID, we are trying to find the right position for this element, right? So which is going to be at position 4, right? This is at position 4. So when we say partition index, it will allow us to look at elements which are to the left to be sent out for sorting, and to the elements that are to the right to be sent out for sorting, right? So that becomes the partition ID here, right? So when you say partition ID, anything that is to the left needs to be sorted, and anything to the right needs to be sorted. However, the actual partition ID itself is at its final resting position. That's what it means, right? So the whole idea is that we identify a pivot point, and we pivot that point at the right partition ID or index, right? So that's what it means. Yeah, I just wanted to make sure I shared that with you, because that's going to be one of the key concepts here as well as we go ahead to the coding part. Okay. I'm going to go ahead and close some of these other items so that there is no visual distraction for you folks. Okay. All right. So our function, the main function, is going to be called the quicksort, right? So I'm going to say const quicksort. It's an array is a left pointer, and the other one is the right pointer. All right. So when we want to run this quicksort, we want to run this when we want to run this. So when do we don't want to run the quicksort? Can you tell me? We don't want to run this quicksort when there is only a single element, right? So if there is a single element in the array, there is nothing to do. It is already sorted, right? So how can you identify there is a single element? Whenever left is equal to right, correct? So I want to run this quicksort only when left is less than right. Okay, I want to run the quicksort only during this condition. If it is any other thing, if it is left is more than right, obviously we don't want to run this. If left is equal to right, it means it is already sorted, right? Okay. All right. So what I want to do, first thing is I want to find the partition index, right? This is where I identify a pivot and find out the partition index, right? So say const partition index is equal to, I'll call the method that is partition. This is going to be another method. And I'm going to pass the same set of arguments here as well, array, left and right. Okay, all right. And once I get the partition index, right? So remember, I showed you in this diagram here, when we send this data for partitioning, what happens? We will choose phi as the pivot, right? And we will come back with the partition index. So right now, the partition index here is going to be how much? 4, right? The index of phi after it is gone through the first level of sorting, it'll be placed here. The index here is going to be 4, correct? And that is going to be it is going to be 3. Oh, we are starting at 2. This is 0, 1, 2, 3, and 4, right? Okay, all right. So essentially, we will get the partition index of 5 here, right? So I'm going to go here and then get the partition index, right? So, and what do I want to do? I want to run quick sort on data which is less than this partition index and more than this partition index, right? So essentially, it is going to be a multi-branched recursion as we call it out here. So I'm going to say quick sort, and I'm going to start with, I'm going to pass the same array, right? Right. And for the left, right? For this one, the left is going to remain the same, right? So we'll retain that, right? And what is going to be our right here is going to be the partition index minus 1, the previous element to the partition index, right? So I'm going to say partition index minus 1. Right? This is going to be sorting of our left, the left part of the array, right? And we also want to do this for the rightmost part of the array, right? So this is going to get the array, right? And what is going to be our left here? Can you tell me what is going to be the left here? You can go to the diagram and tell me. So this is our partition index. Yeah, absolutely. Yeah. It's going to be partition index plus 1. And our right is going to remain the same, right? All right. Okay. This is all that there is to it for the quicksort algorithm itself. However, the key aspect will be in the partition method or the partition function, which is going to have do a bulk of the work. Okay. Okay. So let's go ahead and then write that one. So I'm going to say const okay. I think I lost my cursor here. Okay. So I'm going to say const partition, and this is going to get the arguments array, left pointer, and the right pointer. Okay. All right. Okay. So what do we do? First thing we want to do is identify the pivot element, right? So I'm going to say const pivot element is equal to, this is going to be the rightmost element in my case, right? So I'm going to say array at right. Right. And I also want to define my partition index, and I will essentially initialize it to the first element here, right? I'm going to say let. This is going to change, by the way, as we scan through the array. So I'm going to essentially say let index just make it IDX just to keep it short. It's going to be equal to the left. Okay. Oops. Okay. So what I do, I maintain 2 pointers here, essentially. One is going to be the left pointer, and the other one is the partition index, right? So I'm going to have 2 pointers here. One that's going to run through the entire, scan through the entire length of the array, and the other one, which is going to be for the swapping of the partition index itself, right? So I'm going to say for let j is equal to left, okay, j less than right, because right is the pivot, right? We don't want to go to the right. So I'm going to say j less than right and j plus plus. Okay. So I'm going to say if the array element of j, right, is less than the pivot element, than the pivot, what do? We want to do a swap here, right? So I'm going to say swap array, and I want to pass the partition index, and j. Okay. And I also want to move the partition index by 1 here. Remember, we have 2 pointers. One is a partition index pointer, and the other one is a j. J anyway is taken care of by the for loop, but we need to manage the partition index ourselves. All right. So this is the part where the swap happens, right? So we also need to make sure that we have a swap method here, right? Okay. So, and at the end of it, all our element, so for the pivot to be the final, to be in its final resting point, what we have to do is we have to go ahead and swap the partition index with the pivot element itself, right? Which is going to be at the right. So I'm going to say swap array partition index and the right. Okay. All right. So let's actually look at what the swap itself is going to do. And of course, at the end of it, we also need to return the partition index here, right? Because our quicksort is waiting for that, right? So we can say return partition index. Okay, let's go ahead and write the swap here and say const swap is going to be equal to, it's going to be an array. And of course, we get 2 pointers, I and j. Essentially swap them, right? So I'm going to say status swap const temp array at I, okay, and then array at I to the array at j, and array at j is going to be equal to temp, right? This is how we do this swap. Okay, all right. So this is all that there is to it, right? So essentially, we started off with the main function of the quicksort, right? Which is essentially looking for a partition index, right? And when it finds a partition index, it does the quicksort on the left half of the partition index and the right half of the partition index, right? And this is going to repeat over and over again until the number of elements become 1, right? At which point the left becomes more than right or equals to right. right? And the important part here was the partition method itself. So essentially, we are going through the entire array, starting from 0, right? And anytime the element at left is less than the pivot, we essentially swap the swap both the positions, right? And we increment the partition index here. If it is not greater than the pivot, we don't do anything at all. Okay. All right. So let's go ahead and run this one. I'm going to go here and hopefully it's going to run all right. So I'm going to say const array r1 is going to be equal to 6, 3, 2, 1, and 9. Let's take this one. Okay. And I'm going to call quicksort on this one, right? And say quicksort. And it's going to get the array 1. Okay. And how do we want to start? We want to start at left of 0 and the right of our length of -1, right? Array length -1, right? This is what we want to do. Okay. So if I do this right now, of course, I need to console log this one. If I do this, and then of course, I need to console log the array, of course. Okay. So I can do a console log right before console.log of array1, okay, and console log of array1 right after. So I can just properly make it explicit. It's going to be before, right? And this is going to be after. All right. Super. Let's actually run this one. Hopefully there are no issues here. Okay. I'm going to say node. Are we in the right position? Quicksort. Yeah, we are. Okay, there we go. We have 63219, which was the original array, and 12369 is the sorted array, right? Okay. All right. So coming back to the complexity here, right? So we are doing the just a minute. I'm trying to get this one to okay. So we are running through the entire array here, right? So if you look at it, we are running through the entire array, right? So essentially, obviously, it has to be n, and we also do this log n times because we are dividing the array to to different partitions, right? We're partitioning it here, and then we are running each partition n times, right? So that means it is going to be n log n, right? Okay. And obviously there is no space complexity here because it is all happening in place in without using additional space. Okay. Make sense? Any questions, folks? Are you with me? Can we move on to the next problem, or you want to take a quick dinner break? Up to you guys.
Sir, you need to scroll the chat.
Sorry? Oh, okay. Sorry. I thought it was auto scrolling. Line left, line 28. Okay, you wanted to look at the partition function. Okay, all right. Line 28, why out of for loop? Okay, let me go back to the code. So you're saying line 28, is it? Oh yeah, it cannot be out of, it is not out of, is it out of for loop? Yeah, it has to be out of for loop only, na? It has to be out of for loop only. Because if you put it in the for loop, it will be because ultimately we want to saw. We don't want to touch the right inside a for loop, right? Only when everything is sorted, then we actually touch the rightmost pivot element and then swap it with the partition index, right? Correct. Because if we push it to here, I think that's not going to work, right? Because we are already doing it here. We're already doing the swap here. There is no point in doing it one more time here, right? Okay. All right. What is the other question? Okay, partition function we wanted to explain. Okay. So essentially what's happening here is that let's assume that we get this. I'll try to explain it as much as I can. I'm going to take this example. So 6, 3, 2, 1, and 9, right? Okay. So here, what do? We actually try to find a pivot, right? So this is going to be a pivot in this case, right? So in here, what do? We actually try to find the partition index from these elements, right? Okay. So essentially what happens is that in this case, 9 becomes the partition index itself, and there is nothing to swap here because that is where its final position is, right? So what do? We actually run the function, right? The quicksort function on this particular block, right? And we choose 1 as the partition index, right? And when we choose 1 as the pivot element, we try to go through this entire length of the array except 1, right? And we check if this element is less than this. It is not less than this, right? So we don't do anything. Similarly, we check if this element is less than 1. It is not, right? So we don't do anything. Similarly, we check 2 is less than 1. No, we don't do anything, right? So what happens finally? We have not swapped anything, but our partition index is still here. So what happens? We swap the right with our partition index. So essentially 1 comes here, 3 here, 2 here, and 6 here, right? And 9 anyway is already here. Are you getting it? Okay, so I'm referring to this particular code which I wrote here. Allow me to share that again. Okay, I'm referring to this part. So if array at j is less than the pivot, then we're swapping. Otherwise, we're not swapping at all, right? Only after. That's what we did here when we swapped 1 with 6, right? Okay. So let's say we want to do a quick sort on these numbers, right? So we take 2 as the pivot element now, okay? And we say this is going to be our partition index to begin with. So I'm saying is 1 less than the pivot element? It is not, right? We don't do anything. Is 3 less than the pivot element? Then we swap it 3 less. No, actually 3 is more than 2, right? What was the logic here? So you're saying if array j is less than pivot, right? It is not, right? So essentially, after no swaps happen, but at the end of it, we swap. Okay, actually, 1 is less than 2, right? So hold on. So 2 is a pivot element, so our stuff will only run from here to here, right? So we don't essentially 1 is less than 2, right? Or j is less than 2. So we do the, yeah, we do the swap here, and then we increment the partition index as well. So we do the partition. So we actually swap it with this one and then do the partition like this. So partition index becomes this one, right? And so now again we go back here and check if array j is less than pivot. It is less than pivot, right now. So what do? We don't have anything to swap right now. We have reached the end of it. So what do? We swap the partition with the pivot element, right? So essentially it becomes 2, 1, and 3. Okay. So right now 3 is in its final position. Okay. 3 is in its final position, and we then, oops, I'm not getting my cursor for some reason. Okay, so 3 is actually finally in its position. 6 and 9 were already in the final position. Okay, I'm not sure why I'm not getting the cursor here. Okay, cursor is going away for some reason. Okay, 6 and 9, they were already in their correct positions, right? We don't touch them here. So similarly here. So right now 3 is also in its final position. Oops, can't seem to get my cursor for some reason. Something is wrong. Is that the issue? Okay, yeah, there we go. So 6 and 9 are already in the right position, right? And 3 is also in the right position. So we run our quicksort on this one right now. So what happens? We start this as the partition index and this as the pivot, right? So what happens if 2 is less than, we check if 2 is less than the pivot. It is not, right? So finally, we swap these two elements, right? We swap these two elements, right? These were already in their right position. And then we look at the elements which are next to this 2, which is going to be only 1. And this is going to be only 1. So we don't run our quicksort anymore because left is going to be equal to right. Correct? That's how it runs. Making sense, folks? The partition index, how it's going to work. So essentially, we're going to start with this array, right? The partition index initially is going to be here. This is going to be a partition index, right? We start from left. This is going to be a pivot element. Is 6 is greater than 9? Is that what we're checking here? If 6 is less than 9, then we actually swap it, right? Yeah, not less than 9. 6 is less than 1, that is, because 9 we will never compare it with if 6 is less than pivot, then we swap the array. And here j and the partition index are the same, right? So we don't do anything at all, right? And then we actually move the partition index to here, right? Similarly, if 3 is less than 9, what do? We swap it again, right? So we end up with this particular array at the end of it all. Okay. Yeah, actually, I suggest you trace through this particular partition index method, and that would give you a sense of what is actually happening there. Because explaining it here sometimes it can get confusing to you, right? Only when you run through that particular function, it will make more sense, right? Yeah, you run that function multiple times, probably with different sets of inputs. It'll actually give you a better sense of what's happening inside. Okay. All right. So I hope I was able to convince and essentially explain it in a meaningful way. But I certainly encourage you to practice it on your own, and it should give you a better hang of how things are happening internally. Okay? Sure. Yeah, I tried my best. Yeah, I'll definitely improve on that. Thanks for the suggestion. Okay. All right. So it's about 9:35. Do you want to take a dinner break and come back? Okay. Thank you. Thank you for the compliment. All right. Okay. So what time do you what do you want? What time do you want to come back? 9:50. Okay. All right. We'll be back by 9:50 then. Cool. Talk to you soon. Hello, everyone. Can we get started? Can we get started? Are you back from the break? Okay. So in that case, we can move on to the another set of problems that we have with us, right? And I think, yeah, we have 4 more problems here, which we need to look into, right? And we'll try to. So what I'm going to do here, though, is look at uh, some of the interesting problems. So I would like to look at the rat in a grid problem and, of course, the search egg problem first, and then we'll move on to the next set of problems, right? Not necessarily in the order that has been mentioned here, but we will take a different approach. So those 2 problems are quite interesting, so I thought we'll attempt them first. Okay? All right. Give me a moment here. I'll just go ahead and then look at this particular thing. So this is going to be part 4. So now we will be moving on to part 5 here, right? So let's see, part 5. Okay. And let's get started. Okay, let's look at the first problem. And that's going to be here. So we'll look at the search egg problem first, and let's take a look at that, right? So that's going to be the third one. So consider an egg tray. Each egg is assigned a unique ID. And in each row and column of the given tray, the eggs are sorted based on their unique IDs, right? And your task is to find an egg with a given ID, right? Does this problem sound familiar to you? Did we come across this particular kind of a array problem before? Do you remember? Yeah, can you tell me which one was that? So we came across this problem, I think, in the part 3, where we looked at the, let's say, finding the number of zeros in a sorted array and sorted. We had issue with that code? Really? No, no. So this problem, right? We are trying to find out in the number of empty cells, right? In an egg tray or something like that. There was some problem with that where we had sorted arrays and sorted columns, right? So essentially that was one part. And we also looked at the kth smallest element, remember? The kth smallest element in a, let's say, in a matrix, the 2-dimensional matrix, in sorted, which has sorted rows and sorted columns, right? Both of them had similar kind of a structure to it, right? So even here, it says in each row and column of the given tray, eggs are already sorted, right? So it is row-wise and column-wise sorted, right? So your task is to find an egg with a given ID, right? So if you look at this right now, each row is sorted and each column is also sorted, right? So we need to find out, given a particular ID, we need to find out the matrix, or rather the coordinates of that particular ID. So right now 13 is at, actually this input is wrong. They say each input is sorted, each row is sorted. It is not sorted. I think this is actually incorrect. This input is incorrect. Can you see? They say in each row and column, eggs are already sorted based on their IDs. So right now, this row is not sorted. This row is also not sorted, and this row is also not sorted. Oh my God, what are we? I think this is actually a typo here. Because if I look here, as per the conditions, eggs are already sorted row wise and column wise, but the input doesn't look like that, right? So I think there is some problem there. Okay. Do you see that? I think there is an issue with that input, this input at least, because they are not sorted. Yeah. Okay. Anyway, with that as the we will take that, the rows and the columns are already sorted, and try to find a given item, right? Uh, with a certain ID, and try to find that out. Okay. All right. So let's get started. Mm, okay. So I'm going to go back to the ID here one more time. There we go. And in here, this would be called, what would I call this? Find egg by ID or something. Yeah, that would be something that we can do. Reasonable name. Okay. All right. So in here, let me collapse the sidebar. And so how do we do? Let's actually whiteboard this, right? So we can, so let's assume that we take some input, our input, right? Mm, okay, allow me a few moments here. I'm having some issue with my screen, so I'm just trying to readjust the focus. Okay. So, oh my gosh. I'm getting the right data here. So let's assume that we have this data. Let's assume we have this data, right? Okay. So this is going to be our data, right? So if I type it out here, let me go ahead and type this out. So this is going to be 10, 10, 20, 30, 15, 40, of course, I missed that out. 15, 25, 33, 45, and 27, 29, 37, 48, 32, 33, 39, 50. Okay, so if you look at this right now, this matrix is sorted in row-wise fashion. It is also sorted in column-wise fashion, and this applies to all the rows and all the columns, right? So if you look at row 2 as well, it is sorted. Row 3 also sorted, and row 4 also is sorted, right? Similarly, it applies, the same thing applies to all the columns as well, right? 30, 33, second row, third row, and I'm sorry, third column, first column, and fourth column, and so on and so forth, right? So how can we do it, right? So last time we looked at this problem, right? So we said we can look at this particular let's say position as the midpoint, right? Because these are, anything to the left of this is always going to be less than that. Anything at the bottom is always going to be more than that, more than or equal, right? So that's what it essentially says. We could either use this one as the midpoint or this one as the midpoint, right? And so and then um, and we'll check if the target, right? Let's say the target is 25. Let's say the target is 25. We'll check if the target is either less than this particular column, or the value at this particular position, or more than this position, right? If it is less, what do? We actually go ahead and what do? We go ahead and decrement the column, right? So we say, let's say this was I and j of 0 and 3. Now the column becomes 0 and 2. So this becomes 0 and 2 now. Okay. So since the target is 25, we check if this one is actually less than or equal to the target, right? This is actually greater than target. So what do? We go ahead and if the current is more than the target, okay, if the current is more than the target, we say column minus minus. So current is, otherwise we say row plus plus. So the current right now is more than the target, right? So we say column minus, right? Which is what we did. So we did that. Current right now is more than the target. So essentially we do another, we decrease the column. So this becomes 0, 1, right? So we come here. Right now the current is less than the target, right? So what do? We want to go down, right? So we say we want to increment the row. So which means this one will become 1, 1, right? And here, and in each step, right, we check if the target is equal to the current, right? So in this case, the target becomes the current, right? So we say we essentially return this position of 1, 1. Okay, is that making sense, folks? Or I can explain one more time in case that was not very clear. Let me know. Do we want to go over this one more time? Are there more? Okay. So so let's say this is the input array, right? This is the 2D array. And if you look at it, this is sorted in row-wise order, also in the column-wise order, right? So anything before this is less than this number, the cardinal number, and anything that comes below this, right? It is always going to be either equal to or more than that, right? That much is given. So what we can do is we can start with this element as our starting point so that we can compare our target with this number. Okay. And let's say our target is less than this. What do? We actually go in the horizontal direction, leftmost direction. If the target is more than that, the current value, we actually go in the downward direction here. Go in the downward direction, right? So for example, let's say our target is 25. We are looking for an element with the target of 25, right? So what do? We check the current is right now 40 because we are starting from 40, right? Because this is our kind of midpoint, if you will, right? So 25 is less than 40. So what do? We actually decrement the column, right? Okay, because current is more than the target, right? Current is more than the target, so we actually decrement the column. Okay, so now the current becomes 30. 30 is more than the target, right? So what do? We decrement the column again. So we come to 20, which becomes the current. So current right now is less than the target. In that case, what do? We increment the row. Okay. And at each point, right, we also check if the element is equal to the current, right? So for example, in this case, the element was not equal to current. The target was not equal to current here. Target was not equal to current here, but here the target becomes equal to current. So we found our ID here, right? So that's how we actually go about solving this problem. So let's take 45 here, or for that matter, let's take 39, right? So we start with 40. So 39 is less than 40, right? So what do? We decrement the column, right? We come here. Now 39 is more than 30. So what do? We increment the row, right? So we come here. 33 is again less than 39. So we increment the row. Finally, we come here. 39 is found here. If target is smaller, we go left, else we go down. Yeah, that is absolutely correct. Okay, that's the logic. So we essentially go down here. So let's assume that we give a number which is not in this particular list. So for example, say this one, right? Okay, what happened to the voice? You're not able to hear me? Okay, great. So let's start with 11. And so with respect to 40, 11 is lesser, right? So we keep moving to the left, right? And finally, we keep moving. We come here, right? And we come here. So right now, 10 is less than 11. So we move down, right? And at 15, it is actually more than 11, right? The current is more than the target. So what do? We move to the left. However, we have gone out of bounds here, right? There is no column before this, right? The column here is 0. If we go here, the column becomes -1. At this point, we want to end our search, and what happens? We come back with an answer of -1 and -1, indicating that the element was not found. Okay. Whenever we find something, the element is found. Let's say, for example, 25 was found here, right? We can return the coordinates of this one, which is going to be 1, 1, right? Which is going to be first row and the first column, right? So that's what we're going to do, right? Making sense, folks? All right. So here, what is going to be the time complexity? So time complexity here would be, at most, we're going to traverse, let's say, m rows and n columns, right? So it'll be m plus n, right? It is not going to be n square, because we're not going to traverse everything, right? We're going to traverse at most m rows and n columns, right? At most, right? So it's going to be n plus n. Okay, so can we go ahead and then code this one out now? All right, I'm going to go back to the IDE, right? So let me go ahead and type this one out. This is going to come in handy for our exercises. Okay, great. So let's get started. I'm going to call this const find underscore egg. It's going to be a arrow function. It's going to get a matrix. It's going to be two-dimensional, and it's also going to get a target. Okay. So first thing is we want to check the bounds here. So I'm going to say const m is equal to the number of rows, which is going to be matrix dot length, right? And we're going to get the number of columns as well, which is going to be const n is equal to matrix 0 dot length, right? So I'm going to say let row is equal to 0. We're going to start with the first row and the last column. Remember, we said we're going to start from here, right? So I'm going to say let col is equal to n minus 1. Okay. All right. And we're going to run this particular function when we are within the bounds of the rows and the columns, right? So I'm going to say while row is less than m and column is greater than or equal to 0, right? We want to do this particular thing. Okay. So I'm going to say const current is equal to matrix at row and column. Okay. All right. So what will be the first thing I want to do? I'm going to check if the current is already equal to target. So I'm going to say if current is equal to target, right? We have found our we have found it, right? We have already found it, correct? So what do? We just return the row and the column. Oops, not undefined. This is going to be target. I return row and column. Okay. All right. So in case if the current is, let's say, greater than target, what do? The current is greater than target. What do we do if current is greater than target? All minus minus, right? If current is greater than target, it's row plus plus or call minus minus? Call minus minus. Okay. I'll just make it explicit here. So I'm going to say if current is less than target, I'm going to say row plus plus. Okay. So that's all there is to it, actually, this particular thing. Okay, and in case we don't find anything, we just gonna say return means the element was not found. So we'll just return negative coordinates here, -1, -1, which means the element was not found. Okay. Right. So let's actually go to town. Should be good here. I'm going to copy this one. Oh gosh, can't. Okay. All right. Let's go ahead and execute this one, right? I'm going to say this is going to be the input. And okay, we say console dot log, and this is going to be find egg, and it's going to be matrix, right? I think that's what's the signature here. Is it the matrix first? Yeah, it is the matrix first. Matrix and the target. So target would be 25 here. Okay, it's actually target 25. Give us back 1 comma 1 here, right? It's 25 here is here at 1 comma 1. Okay. All right. Hopefully we're gonna come back with the. Are we in part 5 here? Okay, need to go to part 5, move out of part 4. Part 4. Okay. CD part 5. Say node, right? ID and 1 comma 1 is what you get here. So let's look for 50. I'm going to make it target is equal to 50. Okay. 3 comma 3, which is correct. Let's look for 32, which is in the corner as well. So it should give us 4. Any questions? Any questions, folks? Any thoughts? Okay, right. So we'll come to the next problem. I'll just get some water to drink. All right. Okay. Great. So let's go to the next problem. I'm going to open up the PDF here. Okay, this was the search egg problem, and the next one would be the rat in a grid problem. Okay, so here consider a grid in which a rat is present in some specific position, right? I need to search that rat. There can be multiple paths to reach that rat. Your task is to count the number of unique paths which are present to reach that rat. Source and destination will be given in the input. Destination is where the rat is present in the grid. And important point, we can only move in the right and downward direction. Okay. All right. So what is it that we are given? Let's discuss that. This is actually an interesting problem. So we are given a let me draw this one out here. So where's the example here? Let's actually take a look at the example, right? So I'm going to go back to the example where it was. Okay, there we go. Okay, so we are at, so this is one of the input arrays, right? Since again, this can be anything actually. The numbers can be anything, right? And essentially we are at 0, 0, which is 11, right? And we need to find ways to reach 16 where the rat is present, right? So if I take this example, let me actually make a note of it, right? So this is going to be 11. So the input here is going to be 11, 11, 12, 13, 14, 15, and 16, right? So remember, this is our starting point, let's say, right? So this is going to be our source, right? And this is going to be our destination, let's assume, right? It could be anything, but for our discussion purposes of our discussion, this is going to be a source and this is going to be destination. So how can we reach the destination from the source? How many ways can we find out? So I can, let's say, and remember, we're only allowed to go in left, in the right, and downward directions, right? That's what they mentioned, if I'm correct. So you're only allowed to go, yeah, you're only allowed to move in the right and downward direction. That's what they mentioned here, right? Only allowed to move in the right and downward direction. Okay. So here, so let's actually try moving in the right direction, right? So for example, we are here, right? So let's assume that this is our position, right? So if we go to the right, what do we get? We go to 12, right? From 12, we can go to right as well, right? So we reach 13, right? From 13, we cannot go right because it's already at the end of the bounds, right? So we can only go down, right? So we can say we can go to 16, and 16 is our destination. So this is one way, correct? Similarly, let's say from 11, we can, from 12, we can go to right. So this is all, hold on, this is all right. This is right. This is right, right? And from here, we can go down, right? From right, we can go down, which is going to be 15. And from 15, we can go right again, which is going to lead us to 16. So that is another way of actually reaching the destination, right? And also from 12, what can we do? We can go right from 12, right? I think that's what we did. Okay. So from 11, we looked at going to 12, and we can also go down from 11, right? So for example, we can go down from 11 and we reach 14. And from 14, we can only go to the right because there we cannot go down. So we go to 15. I'm sorry. So from 14, we can only go to the right, not to the down. Sorry. So from 14, we go right and we reach 15. And from 15, we cannot go down. We can only go right and we reach 16, right? So we have how many ways? 3 ways, right? So one is from here. Oops. So go from here, go this way, go from here, go this way, go from here, come this way, and go here, right? So we have 3 ways of reaching the destination, and that's what we're looking at right now. Okay, so this is going to be the essentially ask from this problem. We are given a source and we are given a destination. We need to find out how many ways we can actually reach the destination. Okay, all right, and this is going to be, again, we have to find. So if you look at this one, right, what kind of a problem do you think it is? This is going to be an exhaustive search problem, right? So essentially, we are looking at all the options that are available to us, right? And then finding out different ways, a total number of ways, right? So this is going to be a exhaustive search problem, right? Or also combinatorics, right? We're trying to find out different combinations to reach a particular destination. So in this case, the combination was 12, 11, 12, 15, 11, 12, 13, 16, right? 11, 14, 15, 16. These were different combinations that can be used, different ways that can be used to reach a destination from a particular source, right? Okay, so let's go to the IDE and then start coding this one out. So I'm going to call this by name find underscore egg, not find rat. Yes. Okay, super. So let's actually get going. So I'll have a main method here, okay, and I'm going to call that find. This is going to be an arrow function, const find underscore rat, okay, and it's going to be a matrix, right? And this is going to get a source and a destination, right? These are going to be coordinates, right? So traversal in DFS. So I'm going to have a method here, which is going to be a helper method. I'm going to call that traverse DFS. Okay, and it's going to get the matrix, source, and the destination. Okay. All right, that's all that it will do. And finally, we'll go up here and define this DFS function, const traverse DFS, and it's going to get matrix, right, and source and destination. Okay. Okay. All right. Also remember, we're only allowed to go in a particular direction, right? So I'm going to have a storage or a variable that maintains those directions. I'm going to say const directions is equal to, it's going to be an array. So how do we represent a up here or downward direction? Downward direction, how do we represent this? When we go downward, what happens? So for example, if I go back to this one, if I go downwards, what happens from here to here? The row changes, right? The x-axis changes, right? The row changes, right? Okay, so I represent that with +1 and 0, right? This is going to be a downward direction. Right? Similarly, we have an upward direction. What happens when we go upwards? Not upwards, I think right direction, right? So if you go to the right, what happens? What changes? The column changes, right? So the column increments by 1, right? But however, the row remains the same. Okay, so I'm going to say this is going to be 0, 1. Okay, and this is going to be right direction. Okay, all right. Okay, so let's get started. So we want to find the number of ways, right? So which means we need to maintain a count here, right? So I'm going to say let count is equal to 0. We'll instantiate that to 0, initiate that to 0. Okay, and from the source and the destination, recall our source and destination will be coordinates, right? So if I go back to the example here, our inputs will be these coordinates, right? So we need to destructure that. So I'm going to go here. I'm going to say const source of x, right? And oops, not screen x, source of x and source of y equal to src, right? This is how I'm going to destructure them. Similarly, I'm going to say, oops, there is a typo here already. Const, it's going to be destination x and destination y is equal to DST, right? So I destructure both the source and the destination. Okay. So what's going to be our base case here? The base case would be if the source x is equal to destination x and source y is equal to destination y, right? If both of these are equal, and we can say we have found a way to reach the destination from the source, and we can say return 1, right? Okay, all right. And then what do? We look and then we go in different directions, right? So we have a directions array. So we'll say for let direct dir of directions. Okay. We go in all directions which are specified in the directions. Right now it is only downward and right, correct? So we can say we'll first capture the coordinates of the direction. So I'm going to say const dir x comma dir y is going to be directions, right? Okay. So this is going to give, depending on whether it's a downward direction or the right direction, it'll give us either a 1 0 or a 0 1, right? Okay. All right. Then from here, we'll check what is the new direction. So I'm going to say const new direction. It's going to be equal to, right? I'm going to say source x plus dir x and source y and dir y, right? So we're adding the direction coordinates to our source coordinates, right? Okay. And at this point in time, we also want to check if this is within the bounds, right? So I'm going to have to define another method here. I'm going to say if bounds check successful, bounds check. I want to make sure I'm not going out of bounds, right? So I want to essentially say, give the coordinates here, not the coordinates, the actual bounds here, right? So the bounds would be obviously matrix dot length, right? And matrix 0 dot length, right? It's going to be your m and n values essentially. and of course the new direction, right? If bounce check is actually passing, what do we want to do? We want to call this recursively, right? Right, where did we go? Yeah, we want to call this method recursively, traverse DFS again, right? And remember, it is going to give us some value, right? Which is going to be the count. So I'm going to say traverse DFS. Okay, it's going to get the matrix, right? And it's going to get the new direction and the same destination. And it is also going to give us something back, so which we need to capture somewhere. So, and that's going to be the number of ways. I'm going to say count now is equal to plus equals this, right? So remember, the base case is met, it returns 1, right? We need to store that, right? So essentially, we increment the count here, okay? And so we do this in a loop, right? And after the loop actually concludes, after this is over, we just go ahead and say return count, right? And count. So if I go up here right now, we need one method to check the bounce, correct? So I'm going to go ahead at here, right? And this is going to be equal to the, what are we getting here? Okay, can you hear me all right? Is it okay? Okay. All right. So bounce check will get the I and j values, or rather the m and n values, and the new direction, right? So I'm going to say m and n and then the new direction. Okay, and this is going to essentially on a boolean. Okay, all right. Let's see how we can do this. I will probably make it more descriptive. We'll say position. Right? Okay. So from the position, we'll get the row and the column. So I'm going to say destructure the position here. Const row comma call is equal to position. Okay. So what I do, if row is less than 0, right? It cannot be less than 0, or row is greater than or equal to m, or column is less than 0 and column is greater than or equal to n, right? In all these cases, what do? We are out of bounds, right? So I would say return false, right? Essentially, the bounce check has failed here, right? If the bounce check has passed, we'll say return true. All right. So what we in here, we're calling the bounce check. If it is true, then we're going ahead with the recursion. Otherwise, we will ignore that direction, right? So if I go back to this diagram, so let's say I was here, right? And I was here, and let's say I was going in the downward direction, right? So which means I would be essentially incrementing the row, which would be out of bounds, right? So this particular condition here Yeah, this particular condition, right, will kick in, correct? This particular condition will kick in. So in that case, I'll say return false. When it returns false, it will reject that direction, right? It will reject that direction and essentially go to the next direction, right, from the directions array, right? Okay. So, and that will also serve as our base case actually, right? Because remember, we don't have a negative base case here. We only have a positive base case. This will serve as our negative base case as well, right? Okay. All right. So I think that's about it. That's all that we need to do here right now. I don't think there's a whole lot to do after this, because we have looked at the bounce check. We have looked at the traversal of the in a DFS fashion, right? And made sure we're getting the count, right? So yeah, we're looking good here right now. Okay. So coming back to the complexity of this one, right? So right now we are, so if I go back here to the diagram, at each position we take two, there is a branching factor of 2, right? And we can have a height of at most n plus m, right? So that means we can have a let's say a complexity of, it's going to be a exponential complexity, right? And this is going to be equal to 2 to the power of n plus m. Okay. Actually, hold on. This is not going to be 2 to the power of n plus n. This is going to be, so how many we have? This is going to be 2 to the power of n, actually, which is the number of, yeah, n plus m only, because we are branching in, twice, and also at the same time, the we're branching m times, right? So we're branching 2 times. At the same time, that's happening for n times, which is the number of columns, right? So if you see, we have 3 recursive calls here, 1, 2, and 3, right, at all times. But we're also branching twice at each node, right? Okay, at most, that is, right? So that's going to be 2 to the power of n plus m, and the space complexity is going to be the height of this tree at any point in time. So that's going to be order of n, right? So that's going to be order of n. That's going to be the height of the tree. Okay, so this is going to be the space complexity. This is going to be the time complexity, right? Okay, making sense, right? Okay, so let's go ahead and actually run this program, and hopefully we should be good to go here. So I'm going to essentially say, do we have any inputs here? Don't think we have any inputs. There is nothing to run, actually. So I'm going to say const input. We'll get the same input as mentioned in the document. I think it was actually 11, 12. So 11, 12, 13, 14, 15, 16, right? Okay. So 11, 12, 13, right? It's going to be 14, 15, 16. Okay, super. And what else? And we also need the source and the destination, right? So how can we give that? We can say const source will be 0, 0. Okay, we want to start from here, and const destination is going to be let's say 16, which is going to be 1 comma 2, right? So what is the answer that we're looking at here? Dot log find rat. Okay, we get the matrix, source, and the destination, right? So what is the answer that we should be getting here? Any guesses? Yeah, that's right. So actually, we forgot to do one more thing here, which is to check the bounds itself, right? The source and the destination. If it's so if the source and the destination, right? If there are out of bounds, I think then also we return a 0 here. So we can say if bounds check of, let's say, what does it take here? M and N and the position, right? So this is going to be matrix. We should store them in some central place so it's doesn't get repetitive, right? It's going to be matrix 0 dot length, right? And of course the source itself. If bounds check fails, right, for the source, right, what do we do? So the destination, right? DST will return 0 as well, right? Something that we missed out on. This is going to be our negative case. Yeah. First thing that we do. Then we can probably move it down here when everything else is, taken care of. Okay. So let me traverse DFS and okay, so we should be good here right now. So I'm going to go ahead and clear the screen and run this program. So I'm going to say node find score rat. Okay, matrix is not defined. I think it should be input. Okay. Hopefully that should be good this time around. Let's see, undefined. Why? Okay, we forgot to return here, so this has to be returned. All right. Let's try one more time, and that's 3. That's the correct answer, right? So let's try a few more things. I'm going to try give a position 0, 0, and 13, right? Or for that matter, 15. How many ways would be there if we give 15? So this is going to be 1 and 1, right? How much would that be? Any guesses? Any guesses? How many ways would there be? If you want to go from 11 to 15, how much would that be? That would be 2, and we get 2 here. Okay. All right. And let's give some out of bounds here. Out of bounds, for example, I'm going to give it 3, right? Which is essentially the number of the fourth column, essentially. So we should get 0, right? Yeah, there we go. We get 0. Super. What else? Do you think of any other input that we can give here? We can also give something like, what happens if I say 1, 1, and 1 comma 1. If I give the same, right, what should I get? What do you think I should get here? 0? Are you sure? Are you sure? Let's go back to the code. Yeah, let's go back to the code. So what are we saying here? If this is equal to, if the source and destination are equal, it should return 1, right? So it will return a 1, hopefully. Let's check. Yeah, it does return a 1. Okay. So yeah, this is looking good so far. Just checking if there is anything else that we missed out on. Yeah, actually, you can also use this, similar kind of a thing to solve other problems of this nature. Say, for example, a maze, finding somebody in the maze, and you could use different directions. Right now, we are only using downward and right? So we could also use upward directions, or for that matter, left directions, right? Or it could be even diagonal, right? You could also move in diagonal fashion, which is also going to be one of the directions, right? So likewise, accordingly, you have to choose, you have to make these adjustments in the directions. Okay. All right. Super. So, okay. Any questions, folks? Okay, great. So I think what we may have to do is, we may have to come back one more time because there are 2 more problems here. I don't think we'll be able to complete them today. That's going to take a lot of time. And I don't want to stress you out too much on the same day. So we may have to come back another day to complete that. Okay, right? So I hope you're all okay with that. End of the day, I want to make sure that we don't. Yeah, actually, yeah, ideally there should have been 5, but I will talk to the SSM saying that we'll need additional time to cover some of these topics because obviously these are advanced topics and sometimes there is a possibility it spills over, right? Because there is a lot of detail involved here. It is going to take sometimes additional time. So I'm sure the SSM would agree to have another class, schedule another class, and we can actually look at the another remaining set of problems. I don't think there are many. I guess we might need um, an hour to hour and a half at most, I'm thinking, right? Okay. And I will also make sure that the code base is ready for you to use at that point in time. Okay. All right. Any questions? Any thoughts? Any comments? Yes, that will be the idea. So possibly tomorrow, when we meet tomorrow, or whenever the SSM schedules the next class. Again, so this code that I have used here is some of it is slightly different from what is there in the links, right? So you might find that difference. So bear that in mind. Okay. Yeah. Yeah. Sure. Absolutely. So you might find a difference between the links that are provided in the exercises and the code that I have used here. There would be definitely some difference. So, you can use both of them to understand, in my opinion, right? So which of the problem set did you like the most? I understand the first let's say 2 classes were relatively lesser complexity problems. I think from the 3rd onwards, I think the complexity started to go up a little bit, right? Yeah, the first two were relatively simpler, in my opinion. The second one is where we looked into, let's say, I think we looked at binary search. We looked at mostly the binary search, and then we looked at exhaustive search, um, which was essentially the looking at multiple permutations and combinations, right? Those kind of problems as well, right? And we also looked at the optimization problem as well, right? So how do you optimize in case of dynamic problems, right? The dynamic problem itself, which we looked at, I think yesterday, was it yesterday or day before? One of those days, right? Yeah, this problem was interesting too. Yeah, I totally agree with you. Okay, go ahead. How to check the constraints? The constraints will be given as part of your question, right? So in this case, the constraints would be um, the bounds of the array, so we can derive them. In certain cases, it'll be explicitly mentioned, right? So here, the constraints are the directions. Those are the constraints. And the bounds of the array are the constraints, right? And we are checking the constraints with the directions in the bounds check, right? So yeah, again, constraints would be different for different problems, right? In this case, the bounds are going to be the constraints. We have to be within a certain bounds when it comes to moving, let's say, to the downward direction or to the right direction, right? Any other questions, folks? Okay, great. So yeah, I guess we may have to come another time and essentially look at the remaining set problems. I think there are barely two of them right now, and we can take a look at them and essentially wind up. And if you have any additional questions, we'll also address them. Right? We can then close this particular series after that. Right? Is that okay? Okay. So yeah. So I hope you found this session meaningful and helpful. Right? I know these problems are actually complex actually. So for example, the quicksort one, to essentially explain that in a very meaningful way, even for me, it is challenging. But I hope that you actually go through that code and then run that code to understand these essential logic behind that particular code, right? Finding the partition for the quicksort, because that's going to be the heart of that particular algorithm, right? How we do the partition, and based on that, how we do the divide and conquer. That's going to be key for the quicksort, right? So, and hopefully, you can go back and then revisit that code, and then try to get to the skin of that code, and then understand it in better detail, right? Only when you do that yourselves, you'll begin to understand what's happening behind the scenes. I can explain it endlessly, but yeah, at some point in time, when you actually touch the code, is when you actually understand it, in the right in the right way. Okay. The more and more you actually try to practice it, the better your understanding will become. Okay. All right, so we can close this call today and we'll come back again, and then, okay, that's good to know. That's good to know. So we can close the call today, and thank you for your time, and hope we'll have a good rest of the evening. Okay? All right, good night. Bye, everyone.